Hi, I'm Will. I'm 1/5 of TALUS, a robot we designed for our biologically inspired robotics module. With me in the group is Tom, Ilya, Sam, and there's another Sam in there as well. In this video, I'm going to be talking you through our design process as well as the finished product that we ended up with. So TALUS is a snake, and by moving its body in a sinusoidal motion, it can move itself forwards. The way it differs from other snake robots is that all of its joints are controlled by tendons. So rather than there being a motor on each joint, all the motors are in one contained section and tendons drive all of it. What we've also been able to do is electrically controlled anisotropy of friction, with solenoids pressing into ball bearings and stopping them from rolling when we need them to increase friction with the ground.
Hi, Will from the edit here. Just letting you know that anisotropic means having a physical property which has a different value when measured in different directions. In our case, that's high friction in one direction and low friction in the other. Once we built our first proper prototype, the next step was to check the viability of the design. We did this by checking that the servo motors could move more than their own weight. As you can see here, they are more than capable of doing that. This design wasn't without its setbacks though. We did have some parts break, which led to some reprinting and redesigns as well.
With the next prototype we made sure to streamline the base so that when it came time to move forwards, we could just slap a bottom on and it would move forwards, no worries. We still had a problem with the tendons at the end being so tight that they caused an upward bowing of the whole snake at the end, but hopefully in future iterations we'll add some weight at the ends there and they will just bend themselves back down. The tendon management is still an issue. The tendons are all rooted centrally and they start wrapping themselves around each other and then they lock up and nothing moves at all, so we need to figure out a solution to that. When running at full power, the tendons slip off the guide wheels, so we need to figure out a way of keeping them on the guide wheels because once they go, the whole system breaks.
This is the construction of the final prototype. The vertebrae now have skins on the bottom, which places them in line with the base. The stringing of the tendons for this prototype took 3 hours, hence the time lapse. Here you can see me testing this prototype. The friction between the tendons is too great, as well as the speed of the servos being too low. With all that aside, you can see the snake is attempting to move into a vaguely curved form, if you squint. It was at this point we had a small crisis. We thought we'd broken all 6 of our motors, either through asking too much of them or general overstressing. None of them were accepting PWM inputs. As you can see from the tests, nothing is moving as required. We did solve the problem eventually though. So we had a mini issue. The PWM wasn't working on any of the servo motors, and then we realised that the power supply and the Mega didn't have a common ground. So, we fixed that now. For anyone confused, in order for pulse width modulation, PWM, to work, the power supply and the microcontroller that are controlling the servos have to have a common 0 volts line. Otherwise they don't have a reference point and nothing works. We looked at this for an hour maybe and didn't see it.
So here we are. To recap, we've got a snake with 6 vertebrae, ball bearings that can be pressed into to control friction, and we've remembered to connect all the wires up as well. So what next? Well, the tendons still are not great. They cause too much friction. So we've redesigned the routing block that goes down the centre of the vertebrae, and we've replaced them with fabric rather than plastic line like we had previously. We've also soldered a board with a load of MOSFETs on, which is going to be how we control the solenoids that deal with our ball bearings. Unfortunately, this board does not control current very well. So when we threw that board onto our really high amp power supply, it put all that current through the solenoids, and they worked, but remember that really high-tech mounting system that we used that was effectively hot glue and cardboard? It melted the hot glue and the solenoids pushed themselves away from the ball bearings, and they just self-destructed basically. So in the final test we don't have those solenoids attached. So we're going to put all of that together, and when we have, this is what we came up with.
So yeah, the snake doesn't move forwards, but that's okay. We're still happy with the motion, and the fact that all the motors are contained in the head. That system, with the motors and tendons, as well as the anisotropic friction system, are both relatively novel concepts. We think it'd be a really interesting project for someone to continue working on in the future. We've done the sinusoidal motion bit, now it's up to you to make it go forwards. Thank you very much for watching. Goodbye.